This is video 3 for the mechanical waves unit. For this one, we're just going to talk about standing waves. These are waves that appear to be standing still. It's a pattern that results when two or more waves of the same frequency, same wavelength, and amplitude travel in opposite directions and interfere. And these have to be waves, not single pulses. They actually have to be waves. And the standing waves, they result from the addition of incident and reflected waves that are confined to a region and have nodes, antinodes. And what we're going to talk about, or what you're responsible for, will be uh, standing waves on a fixed length of string, standing waves for sound for open and closed tubes. And that's all we're going to really focus on. So in a standing wave, it's really cool. I'll show you guys some videos and we'll do some demonstrations. But basically, you'll see something that looks like this right here, where we have these things called antinodes. It's kind of like the crests. And at the center point, we have our nodes. And what this is, you can think of it kind of like constructive and destructive interference. We have constructive interference at the antinodes and destructive interference at the nodes. And the whole time, these will be vibrating up and down. So with a string, we can have different standing waves at different frequencies. This right here is the lowest. We call this the first, or the fundamental, or the first harmonic. And then this one will be the second harmonic, or sometimes musicians will call it the first overtone, and the third harmonic, and whatever. And the reason why we have two systems is because musicians and scientists were developing this at the same time, and they had different languages for it. Now, let's say we have a violin playing, and let's say it's a single note. You may think that there's just one note being played, so one standing wave. However, there's going to be several standing waves on the same string at the same time. And that's really cool to think about, each with its own wavelength and its own frequency. So the sound that you hear from most musical instruments consists of multiple frequencies, and that's what gives each instrument its own unique sound, this blend of standing waves. Now, the possible wavelengths, we want to be able to calculate that, and it's determined by the size of the region to which it's confined. So let's take a look at this. So we got our fundamental, or the first harmonic, first overtone, or second harmonic, so on and so forth. And notice how these are divided up. Now something else, remember that one complete wavelength looks like that. All right, so to get us started, we start with the formula for speed for a wave. Speed equals lambda times frequency. So that means that frequency then must equal the speed of the wave divided by the wavelength. So let's say we're taking a look at the very, very first one, the first harmonic, or the fundamental. That frequency, if we take a look at this, the speed's going to be the same. But if we look at this, this is just half of a wavelength. So take a look at it. It's just this part right here. So when we take a look at lambda, well, lambda would have to be twice this length. So if the string has length L, notice that to make one complete wavelength, it would take twice that length. So that means that for our frequency, for that fundamental frequency, V would be divided by 2L. For the second harmonic, this one right here, well, now we do have a complete wavelength. We do get that complete S curve. So this time, lambda equals L. So how can I do that? How can I get this? Well, if I were to add something to this model, if I were to put an n, and if I were to say that n were to equal 1, 2, 3, so all positive integers, for the second harmonic, if I were to plug in a 2 for n, that would cancel out and I would get v divided by L. For this third harmonic, this time lambda equals 1 plus a half. So that's 3 halves L. For the third harmonic, lambda, this time we got 2 of these. So that's, or I'm sorry, not the half of L. And if you go through there and do the math, if you plug in positive integers for n, we can see that this model would give us the frequency for every single one of those harmonics. So for a wave on a string, the model would look like this. We can take a look at some math when we get in class. Now let's talk about columns of air. An instrument, a wind instrument, is simply a big column of air. And standing waves can occur in this. So instruments like organ pipes, trumpets, tubas, clarinets, flutes, the greatest instrument ever, the saxophone, these are all columns of air. And we have 2 types. We got a column that is open at both ends, that'd be like a flute, and we have a column that is closed at one end. That would be kind of like a pipe organ. So let's take a look at the one where it's opened at both ends. For this to work, we must have an antinode at both ends. So an antinode here and an antinode there. And if you look at it, that's very, very similar to a standing wave on a string. For a string, we must have a node at each end, kind of like to block off that standing wave. For a column of air, we must have antinodes at both ends. Well, because of that, the model's identical. You know, for this first fundamental, the length of our pipe is L, and we kind of get, half of a wavelength here. So one wavelength equals 2L. So the fundamental frequency is just V divided by 2L. For the first overtone, or the second harmonic, whatever you want to call it, here we do get a complete wavelength. It's a little hard to see, but for this one, this wavelength, that would be one complete wavelength as well. So this one would just be V over L. Here we get kind of like a 2/3, or so, so on and so forth. Our model then will be the same as the model for a string. That's nice. You don't have to memorize anything new. Now for the next one, we have a pipe that's closed at one end. So this one gets to be a little trickier. So again, the pipe has length L. And this wavelength, if you think about it, where a wavelength is like that, this really is only giving us a quarter of a wavelength. So the wavelength is 4L, so the fundamental frequency then would be V divided by 4L. For this first wavelength, or this first harmonic, or second harmonic, first overtone, here's half a wavelength and a quarter. So it's like 3/4 of a wavelength. So the first overtone, or the first or second harmonic, would be 3V over 4L. And with these ones, we have to have a node at the end and an antinode at the other end. That's how these work. So for this one, here's this. I got one complete wavelength and a quarter, 1 1/4. So basically, it's 4/5 of L. So we got that. So this model is a little more complicated to try to figure out. But basically, what it's going to come down to, we always want to kind of take a look at our fundamental. So the frequency is going to be V over 4L. And we're going to have our N. But this time, N will only equal odd integers. And again, we'll take a look at some more examples of this in class. All right, that concludes our mechanical waves unit note.